you may recall that we had previously learned that for traditional vector spaces, we can express a vector in terms of any basis of the vector space, not just the standard basis. It turns out we could do that generally too for an abstract vector space. We're going to call such a situation when we do this coordinate vector. So let's define it. Let's let V be a vector space. Let's let B be a basis for vector space V. Now let's take some element V, some vector V from vector space V. Now because basis B is a basis, it spans the vector space and the vectors are linearly independent, we can express vector V as a linear combination of the vectors in the basis. Okay? Not only that, but remember that the coordinates, the coefficients, are unique for a basis. There's only one choice for A1 and A2 all the way to AN that's going to make this equation true. So what we're going to do is we are going to define the coordinate vector for V as those coefficients. Okay, notice we give it a special notation. We put it in brackets and then use the subscript of the name of the basis. Okay. Notice order matters here. A1 is the coefficient of V1, AN is the coefficient of Vn. So if I swap the order in the basis, the coefficients also get swapped. Okay, so really if we wanted to be extra careful, we would call this an ordered basis because the order matters. All right, okay, so that's the definition. Let's do an example. Let's get a feel for this. We want to find the coordinate vector for this polynomial with respect to the given ordered basis B of P2 of all polynomials degree 2 or less. So here's my ordered basis. So I want to express this polynomial, negative 3x squared minus 11x plus 8, as a linear combination of my basis vectors. Okay, so let's say A1 times the first basis vector, negative x squared minus 3x plus 1, plus my next coefficient's A2 times my next basis vector, which is 4x squared minus 2x plus 3, plus A3 times my last basis vector, 2x squared minus 1. Okay, so this is P of x, polynomial P of x. All right, what we want to do is we want to find the coordinate vector for P of x. So the coordinate vector for P of x with respect to basis B is going to be the coefficients that solve this linear combination equation. Because I know basis B is a basis, I know there's only one possible choice for these coefficients. Okay? If basis B wasn't a basis, if these vectors weren't linearly independent, then there may be more than one choice for these coefficients. But these vectors are linearly independent. Basis B is a basis. So there's only one choice for these guys. Okay, so how do I actually solve this then? How do I find A1, A2, A3? Just like how we did for determining if a set of vectors is linearly independent, a set of polynomials is linearly independent, we are going to distribute, we're going to combine like terms, we're going to equate corresponding components, corresponding coefficients, and that will give us a system of linear equations to solve. And that will tell us what A1 and A2 and A3 are. Okay, so I'm going to start, I'm going to leave the left-hand side alone. I'm going to start by distributing A1 and A2 and A3 on the right-hand side. If I distribute A1, I get negative A1x squared minus 3A1x plus A1. If If I distribute A2, I get 4A2x squared minus 2A2x plus 3A2. And if I distribute A3, I get 2A3x squared minus A3. Okay, I'm going to combine like terms on the right-hand side. Leave the left-hand side alone for now. So I have my x squared term, an x squared term, an x squared term. Let's combine them. I get negative A1 plus 2A3. Sorry, let's go plus 4A2 first. Plus 2A3 x squared. Now let's do the x terms, x to the power 1. Just those two. I get negative 3A1 minus 2A2 x. And then finally, the constant terms. So that's A1 plus 3A2 minus A3. Okay? Now, because of like terms, the coefficient in front of x squared on the left-hand side has to be the same as the coefficient in front of x squared on the right-hand side. Okay, similarly, coefficient in front of x on the left has to equal coefficient in front of x on the right, and so on. This is going to give, this is going to tell us what the coefficients are equal to. So coefficient in front of x squared, negative A1 plus 4A2 plus 2A3 on the right-hand side of the equation must be equal to negative 3 on the left-hand side of the equation. Negative 3A1 minus 2A2, negative 3A1 minus 2A2 on the right-hand side of the equation has to equal negative 11, the coefficient in front of x, on the left-hand side of the equation. And finally, A1 plus 3A2 minus A3, the constant coefficient on the right has to equal to 8, the constant coefficient on the left. So I get A1 plus 3A2 minus A3 equals 8. That's my system of linear equations. As a matrix equation, the coefficient matrix is negative 1, 4, 2, negative 3, negative 2, 0, 1, 3, negative 1, times the vector of variables A1, A2, A3. And that has to equal to negative 3, negative 11, 8. Solve this, put it into augmented matrix form. My coefficient matrix is negative 1, 4, 2, negative 3, negative 2, 0, 1, 3, negative 1. And my augmented part, since this isn't all zeros, I need to make sure I add it in. Negative 3, negative 11, 8. Okay, so let's plug that into a calculator and see what we get. Okay, so I have my matrix. First row is negative 1, 4, 2, negative 3. Second row is negative 3, negative 2, 0, negative 11. Third row is 1, 3, negative 1, 8. Okay, and so I get my matrix in reduced row echelon form. And the matrix is 1, 0, 0, 3, 0, 1, 0, 1, 0, 0, 1, negative 2. Since the last column of my original matrix was behind the augmented line, the last column of my reduced echelon form matrix is behind that augmented line. Okay? And so from the first equation here, we could see that A1 has to be 3. From the second row here, the equation becomes 1A2 equals 1. And the last row gives me my last variable. 1A3 has to be equal to negative 2. Okay. So that tells me what I need to find my coordinate vector for this polynomial in terms of the basis. It's just going to be those three coefficients that we found, a1, a2, a3. So as a coordinate basis, expand this again. The coordinate basis of polynomial p of x relative to basis b is 3, 1, negative 2. That is a unique way to identify the polynomial, exactly equivalent to the original definition up here. Might look quite different, but it conveys exactly the same information once we understand what basis b is.